Greetings to you all. This is a podcast or a video lecture here on multivariate assumptions. So as we progress and as we look at doing multivariate analysis, we need to make sure that our data has some certain assumptions, some certain characteristics, if you will. That are important in terms of as we want to analyze the data using multivariate approaches. So in order to do regression, ordinary least squares, and some other things like that, data has to have certain characteristics associated with it. And so there are 4 assumptions that we'll deal with, and we want to just point out here. One is normality. So the data should be normally distributed, and so we want to look for features that would suggest normally distributed data. And if the data is not normally distributed, then we need to correct for it. So we need to do some type of transformation usually to make sure that the data is normally distributed. We also want to make sure that there's not something that we call homoscedasticity. And what homoscedasticity, or that there's not heteroscedasticity, that there is homoscedasticity. And what this is when we have 2 variables, what we want to make sure is that the relationship between the variables stays the same regardless of scale. So you can actually see here where there's as the one variable gets larger, the relationship changes. So that's a problem. Another assumption that we'll deal with is called linearity. So there needs to be a linear relationship as opposed to a curvilinear relationship between the variables. And then finally, when we deal with multiple variables, the error that is associated with the variables, because every variable has a bit of unexplained variance in it. So variables vary, and we want to predict the variability, but the amount of the variance we can't predict can't be correlated with other error in variables that we have. So correlated errors is something that we want to consider and we want to look at. All right, so dealing then with normality. Normality then deals with or refers to the shape of the data distribution for continuous variables or metric variables. It tends to be something that we look at first and foremost. It's thought of as maybe a fundamental assumption for all that we do. So sufficient non-normality invalidates a lot of the statistics that we want to try to calculate. So the F statistic and T statistic, for instance, are things that are influenced by non-normality. Okay, so normality, now because of the central limit theorem, normality is a bigger issue if you have a smaller sample. If you have a larger sample, and as your sample approaches the population size, normality becomes a little bit of less of an issue. So data tends to approach normality with the larger they get. So that's important. Normality also is an individual variable issue. So we don't think of normality when we think about 2 variables working together, but as opposed to that, we think of it as an issue like each variable as itself. All right, so that's kind of the thing that we want to think about when we talk about normality. When we look for checking for normality, we can look at the different statistics that are available for us for normal distribution. We can look visually at charts. So there's something called a histogram. A histogram will provide you the distribution and kind of look at it. And you might have heard of the bell-shaped curve. So a histogram that looks bell-shaped will be what you want to look at. And then also normal probability plots. Normal probability plots are ones, they'll have a diagonal line and you will see all the little different data points that are associated with your data, and you want to make sure that they're somewhere around the diagonal line if possible. Okay, other statistical tests, the Shapiro-Wilks test and the Kolmogorov-Smirnov test are two tests that will be easily calculated. They will help us identify normality. And then when, again, data is not normally distributed, we might be able to do some data transformations, which do not necessarily impair the quality of the data, but they will transform the data and help us make the data become more normally distributed. Okay, so that's a possibility of what we can do. When we think about normality of data, we sometimes consider like the distribution of the data, what the data looks like about its mean. And so two moments beyond mean and variance that we look at then would be skewness and kurtosis. So when we look at skewness, we look at the balance of the distribution around the mean and if the data is shifted to one side or the other. So data heavily shifted towards the left is positively skewed. If it's heavily shifted to the right, it's negatively skewed. Okay, and what we're going to want to do is we're going to look at the skewness. So whenever we run our analysis, we'll get a measure of skewness and we'll divide it by its standard error. And also kurtosis will measure by the standard error, and then we will calculate to see the size of those two values. The z-score for skewness and kurtosis, and then we'll set some expectation or significance level, and if the test statistic for skewness or kurtosis is too great, then we will want to look at and visually inspect the data a little bit more. So sometimes I mention the term moments just as a side note for statistics. Data distributions have what we call moments, and the first moment is referred to as the mean. The second moment is the distribution associated with the standard deviation. The third moment is called skewness, and the fourth moment is called kurtosis, or the peakedness or flatness of the curve. Okay, so these help us describe the data, and they helps us describe and understand whether the data is normally distributed or not. So that's the first assumption that we deal with. The next assumption then is called homoscedasticity, and again, we want to make sure that the data relationships between two variables does not change with the scale of the variables. Okay, so this little graph over here indicates that the relationship is changing as one variable becomes larger, or as the variables become greater. And so we have this thing called the variation of effect and the variation of variance that's taking place here. So homoscedasticity then refers to the assumption that the data that the dependent variables exhibit equal levels of variance across a range of independent variables. Okay, the most cases of heteroscedasticity are a result of non-normality in one or more of the variables. So we might see that some of our variables are not normal, and we want to do some data transformations to correct for this. So as you look at the different size or distance here of this data, what you're looking at is different variances across some supposed mean, and that variance is changing as one variable is getting greater, and that may be the independent variable on the dependent variable. Okay, so the common sources of this then would be different types of variables that are being used. Maybe some type of non-normal or skewed distribution might be there. And again, this is going to violate some of the interpretations that we have of our data. So homoscedasticity is something we want to ensure is there where possible. As we identify homoscedasticity, we do so by, again, we could graphically plot residuals. So that was what we were looking at before when we were looking at the data. So we can do some data plots. Then there's also, though, the common test is the Levine test that would help us measure the level or the degree to which homoscedasticity may be present. Okay, so the Levine test is what we want to do there. Again, how we correct for this would most likely be through some type of data transformation, kind of like what we had talked about a little bit when we deal with normality and non-normal data points. All right, the third assumption is linearity. So again, this is when we have two variables. We're looking at two variables together. We want to make sure that they behave together in a linear fashion. Again, this is especially particularly important for regression analysis. So nonlinear relationships can seriously understate the data that you have, and it can create an interaction or an interaction problem that your data has that's not being identified or being seen in normal analysis. So again, scatter plots will identify whether we see non-linear relationships going on. We may be able to solve this problem of nonlinearity through some type of transformation with either one of the variables or multiple variables that are there. Okay, so linear. So the final area that we want to, assumption that we want to look at would be correlated errors. And so basically, as I alluded to earlier, variables' job is to vary. And we want to try to explain why variance happens and why variables vary. Yet there's always a little bit of the variance that we cannot explain through our analyses. So we have errors, okay, so we think sometimes of that as error or systematic error, where there's stuff or non-identifiable error where there's variance happening that we can't really statistically explain, but we know it's there. The problem is that when we have error in two variables that share the same cause. So there's something causing error in two different variables, yet we have not accounted for it. So that error that's shared between two variables is correlated. That's what we call it correlated error. So error terms of the concerned variables should not be correlated that way. When it exists, it suggests that there's some unexplained, relationship that's happening that we need to account for. So correlated errors then arise from a process that must be treated like missing data might actually be. That is, the researcher must first define the causes among variables that might be relating to the two, and we might need to identify what is the result of this data, this data correlation, and then we try to account for it. So it may be that we have to add variables to that. So maybe we add a variable that would account for this variance that exists between the two variables that we didn't have earlier. So patterns and error terms may be there. Residual plots may help us be able to pick up this recognizable error. Think about in a regression when you have when you have a fairly large R, but then when you go to do an adjusted R square, it goes way down. So you may have like a lot of shared variance between independent variables. Like multicollinearity, for instance, it might have a lot of multicollinearity, and that might be an example of where we have correlated errors. And so, if we have a lot of multicollinearity, but we can explain what's causing the collinearity by another variable, then we bring that other variable in, and the messiness of the model gets cleaned up quite a bit. So that's what we want to think about, maybe dealing with there, when we're dealing with a correlated error. Adding a variable and trying to account for the shared variance between error terms. So normality has to be there, right? That's what we want to. We need to have normality. We need to check for it. We've got to probably do some type of transformation of our data if we have it. Homoscedasticity, dealing with error or variance that changes over the magnitude of our variables when we have two variables that are paired together. So homoscedasticity is when that variance is the same or uniform. Heteroscedasticity is when it grows or changes. That's a problem. Linearity, you have to have linear relationships between your variables. If you don't, we need to do some type of transformation probably to correct for that. And then correlated errors. Again, when you have variables that have error terms and those error terms are related to each other, we probably are missing a variable, and so we probably need to add a variable to help explain that shared relationship between error terms. Okay, so those are the four assumptions. We need to know those four assumptions and be able to deal with them.